So we get this equal to 5 by 18, 6th root of u times v. And so step 3 now is an integration. So now step 3 is writing the integrand. So how will our integrand look like? So integrand is xy. So what is my xy? Xy is simply u. So integration of u, right? So that is the integrand. Now what about the 2D integration plan? So this is your integrand. So let's just, so 2D integration plan. So step 4. So 2D integration. So we have integral from, so since it's a rectangle, let's just write down the integrand first here. So u times 5 by 18, 5 by 18, so 5 by 18 cube root of u times v, and we can do any one first. So let's say du dv. The limits of integration for u is 1 to 2, and limits of integration for v is 1 to 3. So this is the integral, right? Okay. So now under the similar hypothesis, we can describe that if we are looking at f of x by z dv over solid E or solid R, so let's use solid E, then it will be basically this integral f of x by x. So you write x, instead of x, you're writing it uvw, y as function of uvw, z as function of uvw. You replace the volume element. So this is your dv element, gets replaced by this absolute value of Jacobian times du dv dw, and where the generalization of 3 by 3 Jacobian is given to you here. Okay, and this Jacobian is a Jacobian of transformation. X equals to x of uvw, y equals to y of uvw, z equals to z of uvw. So the idea is you're writing it as the Jacobian of this, right? So let's derive the formula for triple integrals in the spherical coordinates. So again, recall, for the spherical coordinates, we had, so we already know the formula, but we want to derive it from this perspective and see if it matches. So what we'll do is the following. So we had x was rho sine phi cos theta, y was rho sine phi sine theta, and z was rho cos phi. Okay. So derive a triple integration. So suppose we want to integrate f of x, y, z dv. We have a solid E. So you can call this R. So we have region R. Okay. So now first step. So our function is given the same way here. So we'll compute the Jacobian. So let's compute the Jacobian here now. So Jacobian is going to be x, y, z rho theta phi. You'll say, what if I permuted the order of, instead of rho, I took theta, and theta, I took phi? Well, you're taking absolute value in the end, so it shouldn't matter. So let's look at this guy. So derivative of this with respect to rho first. So what is that going to give me? Sine phi cos theta. Derivative of y with respect to rho is going to be sine phi sine theta. Derivative of z with respect to rho is going to give me cos phi. Now derivative of x with respect to theta is going to be rho sine phi sine theta with a negative sign. Derivative of y with respect to theta is going to be rho sine phi cos theta. Derivative of z with respect to theta is going to be 0. Similarly, if we do derivative with respect to phi, so we get rho. So we'll be only differentiating this guy. So cos phi cos theta. This will become rho cos phi sine theta. And this will be z rho sine phi with a minus sign. Now we need to compute determinant of this object here. So let's see if we can simplify it by any form, and doesn't seems like. So what I'm going to do is I'm going to expand this determinant based on the last row. So we had plus minus plus minus plus minus plus. So I'm going to expand it using cos phi now, and so using last row. So then it'll be equal to cos of phi. Forget about, so consider this submatrix now, right? So that's gonna be minus rho sine phi sine theta, rho sine phi cos theta, rho cos phi cos theta, rho cos phi sine theta, minus rho sine phi. In bracket we have, now again we'll take this part here, so we'll have sine phi cos theta sine phi sine theta. Then we have minus rho sine phi cos theta, rho cos phi sine theta. Cos theta, my bad, right? So sine, copying the, I should copy this one here. So this one should be here. So in that case, it should be rho sine phi sine theta and cos theta. Now we have to expand it out. So we get cos phi. You can pull out rho common. So we get rho square, right? And determinant, you can pull out the row from each, or you can multiply and check. Then in bracket, we have minus sine phi cos phi sine square theta minus sine phi cos phi cos square theta. And then here we get minus rho sine phi. Again, you can pull out the rho common, so we can pull out sine phi common. And here there was another sine phi. I made a mistake here. This should have been also sine phi, right? Sine phi. So now I can pull out rho common. So rho sine phi. So I can pull out sine phi common from all of them. What do I get? I get rho sine phi. So I get sine square phi. In bracket, I get cos square theta plus sine square theta. So when you expand this out, we get So I should, when I pull sine from both of them, it should become sine q. So now, so we'll take out sine phi cos phi common. So we get sine square theta plus cos square theta, which is 1. So we get cos phi rho square times, then what is left in the bracket, minus sine phi cos phi. And what is left out? So we get, for this guy, we have minus rho sine q phi. So rho, again, we took rho square, so rho square will be here. And now, if you look this up, so we get cos square phi, take rho square common, sine phi common, will be cos square phi plus sine square phi with a minus sign. That will become 1. We get rho square phi with a minus sign. So therefore, our integral will be non s, where s is the bound on theta phi. So s gives us the region in theta, phi, and rho. F of x will be replaced by rho sine phi cos theta, then y is rho sine phi sine theta. Z is replaced by rho cos phi. And for Jacobian, we have absolute value of this. And we have d rho d theta d phi. And if you take absolute value of this, this becomes rho square sine phi d rho d theta d phi. Yeah, as expected, right? So we do get the same volume element.